Alright, in this video we're gonna look at another application called the Newton's law of cooling. And this law states that the rate at which an object cools is proportional to the temperature difference between that object and its surroundings, provided the temperature difference is not too large. All right. So this definition here is something that we call a differential equation. And we're not going to look at it from that perspective that is done in calculus, but we can certainly look at the end product because the end product is modeled after an exponential function. All right. So let's see how we utilize this definition over here. When you get to calculus, you will appreciate how all this comes together. But for now, we're just going to take the end product and work with it because it looks like it's modeled after an exponential function. Okay. So D naught, we define D naught as the initial temperature difference between the object and its surroundings. So if its surroundings have a temperature Ts, all right, and then the temperature of the object at time t is given by this definition over here, saying that T is the temperature at any time. Ts is the temperature of the surrounding. And we're saying D naught is equal to the initial temperature minus its surroundings. All right. So let's see. And then K, we say K is a positive constant, which is dependent on the type of object you're working with. All right. So the best way to do this is to go through an example. Okay. So let's see. It says that do I have enough? I think I don't have enough space to do this, but we'll see. It says a cup of coffee has a temperature of 200 Fahrenheit. So this is the temperature of the object. All right. So I guess I use Ti. I got to use To. All right, to make sure that everything is the same. It's placed in a room that has a temperature of 70 Fahrenheit. So this is the surrounding temperature, Ts. After 10 minutes, the temperature is that. So they give us some conditions. So at T equal to 10, this is T of what? T of 10. Find the function that models the temperature of the coffee at time T. So remember that the definition we had was T of little t is equal to the surrounding temperature plus D0, which is the difference between the object and the surrounding temperature, e to the negative kt. Okay, so if we kind of plug in the information that we know that DO is going to be TO minus TS, which is 200 minus 70, which is equal to 130. All right, we also know what TS is. So in this definition so far, it looks like I'm looking at 70 plus D naught, which is 130 e to the negative kt. So it looks like the only thing that is missing over here is that K, which is supposed to be positive, which also represents the decay rate of that of what's going on in this problem over here. So how do we find that? They give us some conditions. They tell us that when the temperature at time t equal to 10 minutes, the temperature was 150. So if I plug in 10 into this definition here, I get 70 plus 130 e to the negative 10k. And now the only thing that we have to solve is figure out what k is, because all of this is equal to what? 150. So let's start solving. So I have 130 e to the negative 10k is equal to 80. And then I'm going to divide everything. So I get e to the negative 10k is equal to 80 divided by 130. 0.61538. Now, if I take the natural log, remember that k is a power and I'm trying to solve it. The only way to do that is to apply my natural log. E to the negative 10k. Let's go to ln 0.61538. And so applying my properties or laws, I get negative 10k is equal to ln 0.61538 divided, so k becomes ln 0.61538 divided by negative 10. Ln of that gives me that divided by minus 10 gives me 0.0485. Okay, so that means that the final formula is going to be 70 plus 130 e negative 0.0485 t. So that only answered question A. All right. Okay. So let's see. They ended up getting the same thing as I did. Yes, they did. So they got the same thing over here. So that answers A. All right. So A is that. All right. Now let's look at B. B said use the function found in A with t equal to 15. So when you plug in t equal to 15 and you punch it into your calculator, you should be able to get that. And then the other part says use the function found in part A with t equal to 100 to solve the exponential equation for t. So they're trying to let us find t over here. It is an exponent, so you have to somehow go through some logs to get you to do that. So first subtract, so you get 130 e to the negative 0.04855 t is equal to 30, and then divide by 130, divide by 130, and then continue working your way from there onward. So they do have that here. So this is where I am right now. And so you solve out that problem, you end up getting what T is. All right. And D says graph a temperature function and notice what happens at line T equal to 7. So if you sketch this, you need to be very careful because we are starting at somewhere, right? So we are starting, it told us that the surrounding temperature was what? Was 70. So you cannot be below 70. All right. So if you sketch this graph, see what happens. So you're starting out at that temperature. The room temperature is right here. It's going to cool. If anything is going to happen, if you sketch this, the coffee is going to cool all the way to the what? To the room temperature. So it's decreasing. So you can have a decreasing graph, but notice that you got to get to the what? To the room temperature. All right. And after some time, it gets cooler than the room temperature, that's when you can cross that horizontal asymptote. But for now, based off of the problem, you can see that it's above the what? The 70 line until such time where the room temperature and the coffee temperature is the same, and then it will cross if now the coffee is cooler than the room temperature or the surrounding temperature. Okay, so that is it, and I think this is our last lesson for the term. I will provide some worked solutions so that it will guide you in your learning. But that is what Newton's law of cooling is all about. Okay.